Okay, so what we're going to do is we're going to develop a flow chart. We're going to start with the idea that all matter can be classified in different ways. And so one way to classify it is to distinguish whether we're talking about a pure substance or a mixture. And that depends on whether or not this lump of stuff, this lump of matter, can be separated by some sort of physical process. If the answer to that is no, then what you have is a pure substance. Okay, if you can't separate the matter into at least two different, groups of matter, subgroups, I guess you could call it, then it is a pure substance. Now, if you do have a pure substance, that's not the end of the story. You need to decide whether that substance, that pure substance, can be decomposed further by some sort of chemical reaction or chemical process. And again, that question is no, okay? And what you have is you have an element, okay? It can't be decomposed any further by some sort of chemical process. So notice the different processes here. So first of all, separate by a physical process. And then if the answer is no, then can we separate by a chemical process, a chemical reaction?
Yes, indeed.
All right, so what if you can separate it, break it down further by a chemical reaction or a chemical process? Then that's what we call a compound, okay? The name kind of gives it away. It's, a compound sort of implies that you've got multiple things combined together, like multiple elements make up the compound.
Yes!
All right, well, let's go back up to the top here. So let's say that we can separate this matter into different subgroups of matter with a physical process. What we call that is a mixture, okay? It's a mixture. And so if there is a mixture, then it still is not the end of the line. We have to classify what type of mixture it is. So there are two. So the way you figure that out, what type of mixture it is the mixture uniform throughout? If the answer to that question is no, then the special big chemistry word we give for that is heterogeneous. That is a heterogeneous mixture if it's not uniform throughout. And if it is,
yes, indeed,
then we call that a homogeneous mixture. Okay, so all matter can be classified in this flow chart. So let's go through some examples.
Gold!
So let's go through some actual examples here. So let's say I have a bar of gold, and let's go through the flow chart. So first of all, can pure gold be separated into simpler things by a physical process? No, it can't. It's a pure substance, right? It is pure gold. And so then the question becomes, well, can I break this down into something simpler by a chemical reaction? Well, once again, the answer is no, because there's only one element involved in this. That element is gold, all right? Let's do another one. So now we have propane, okay, which, you guys use that in barbecue grills and things like that. So let's say we have, a tank of propane. So the first question is, can that be separated into components by some sort of physical process? Well, once again, no, because it's just one thing. It's one type of substance. Okay, so it is a pure substance. But then we could ask the next question, well, can I break propane down into simpler material or other material by some sort of chemical process? And well, as I mentioned earlier, we know that we use propane in combustion, so I can burn propane. Well, that's going to break it down into its elemental constituents. So it is a pure compound, okay? Because it's got, and the other way to think about that is it's got more than one element in it. It's got carbon in it, and it's got hydrogen in it, right? So that's another way to distinguish compounds from elements. Gold only had one type of atom in it, gold atoms. Propane has different types of atoms in it, hydrogen atoms, carbon atoms, okay? All right, so what about this? We got a bucket of mixed up Legos. So is that or can these be separated into, groups by some sort of physical process? Well, yeah, I can just pick out all the white ones and pick out all the blue ones, and that is a mixture. And it is a heterogeneous mixture because you can just see from the picture that it is not uniform throughout. Okay, the mix is different up here than it is down here, okay? What about something like Windex? Okay, so it's this nice blue solution, okay? It's got the cleaning material dissolved in water in there, right? So that's a mixture, but it's a homogeneous mixture. And you can kind of see just by looking at it, it looks the same. It's uniform throughout. So no matter how many times you cut the sample in half, it would just look the same. So it's uniform throughout. So it would be an example of a homogeneous mixture, okay? All right, so there's one more thing I want you to know about pure elements when we find them in nature, and that is that they typically will show up in either what we call the atomic form or the molecular form. And let me explain with a couple of examples. So first of all, something that we find in the atomic form would be like a vein of gold, as you see here in this photo. So if we could zoom in on that vein of gold, you would see just discrete atoms of gold. Au is the chemical symbol for gold. And so if we could zoom in with a powerful enough microscope, you would just see that this gold exists in nature as a pure element, just as gold atoms. Now, compare that to what we find in for some elements in nature as molecules or in the molecular form. And an example of that is something like oxygen gas. Okay, in nature, we don't find pure oxygen as discrete oxygen atoms. Rather, we find O2 molecules. Okay, what you see is that in nature, pure oxygen is always found as O2. All right, so it's two oxygen atoms connected together with two chemical bonds. And we'll get into more what we mean by chemical bonds later in the course. But it has a formula of O with a subscript 2 to represent that it's a molecule of oxygen rather than like an atom of gold. Right? Two oxygen atoms are connected together to make a molecule of O2. And since this is how we find oxygen in nature, it is one of those elements that when you find the pure element in nature, it's in this molecular form. Okay, and specifically, oxygen is formed as a diatomic molecule. And there are some other elements that I want you to know that also are found as diatomic molecules. And this is the list. So hydrogen, in nature, we find it as H2. So two hydrogen atoms connected together by a chemical bond. Also nitrogen, N2. You saw oxygen, O2. Fluorine, F2. Chlorine, Cl2. Bromine, Br2. And iodine, I2. Oops, all right. So another way to classify matter, and this slide has a couple of important ideas on it that I want to get across. So first of all, I want to talk about the difference between looking at something on a macroscopic level versus looking at something at what we call the particulate or the microscopic level, the atomic or the molecular level. And so this picture does a pretty good job of illustrating that. So if we can look at this, this is solid ice, right? So this is how we would represent it macroscopically. But if I wanted to zoom in to the atomic level, this is how I could represent those molecules of H2O that are frozen into this nice organized arrangement. And that's one thing that's characteristic of the solid state. So this is what the solid state looks like at the microscopic or the particulate level. It's highly organized, things are locked in place. Well, here, back up here at the picture, this iceberg is sitting in the ocean, right? So that's liquid water, liquid H2O. And this is how we could represent that at the particulate or the microscopic level. So they're still the same molecules, H2O, right? But they're not as organized. They're still close together, like the solid. They're still close together, but they're not locked in place. They can kind of flow around one another. So that's a characteristic thing of and it's how you would represent the liquid phase at the particulate or microscopic level. Okay, but then of course in the air, these clouds, right? So this is, a little bit of an oversimplification, but these clouds represent gaseous water molecules, okay? And so this is how we would represent that at the particulate or the microscopic level. So once again, it's still the same molecule, H2O, water molecules, but the characteristic thing that you would want to show at the particulate or microscopic level is the space between the molecules. There's a significant amount of space between all these water molecules. And so that's how we would represent the gaseous phase. So gas, lots of space, liquid, very little space, but they're, not much organization. Solid, there not much space between the molecules, and they are all kind of locked in place, highly organized. Okay, all right. So that was this would be the sort of a macroscopic view of things, and this would be the particulate or the microscopic view of things. And another important idea that is characteristic of these different phases is the energy. And so as we go from solid to liquid to gas, the difference is the amount of kinetic energy. So the reason why the H2O molecules are in the gaseous phase here is because these molecules have more kinetic energy than the liquid molecules. And the liquid molecules have more kinetic energy than the solid molecules. And we'll get into that with more depth when we get to chapter 5, but it's important to kind of get that introduction now. Okay, so this diagram, which is also in your handout, shows you sort of the different energy levels of the different phases and the labels for the different phase transitions. Like if I'm going from a solid to a liquid, I increase in energy. That's what going up represents in this picture. So as we go up, we increase in energy. So, and the name that we give to that is melting, right? Or if I take the liquid and I freeze it into a solid, what I'm doing essentially is I'm taking energy out of those liquid molecules to convert them into solid molecules. We call that freezing. Now, two of the labels that you don't have in your notes, so make sure you notice that and write these down. You can go, if for some substances, you can go directly from the solid phase to the gaseous phase. You don't have to go through the liquid phase. And that we call sublimation, okay? And then the opposite process, if you go directly from the gaseous phase to the solid phase, we call that deposition, okay? So I don't think that either of those words are on your handout, so you may want to write those down. All right, so those are the phase changes that I want you to know, and I want you to know the difference in energy between the different phases. Okay, so just realize that, you know, if I want to go from the solid phase to the gaseous phase, what I'm doing essentially is I'm putting energy into the system. And just the opposite, if I want to go from the gaseous phase to the liquid phase, if I want to condense the gas into a liquid, what I have to do is remove energy from the system. Because once again, it's just increasing kinetic energy as you go up. Let's talk a little bit about, you know, if we have matter, we're classifying it. We said that if you can use a physical process to separate out the components, then that is a mixture. So let's talk about some of those processes. And it's related to something that I hope that you refreshed your memory about when you did the pre-class assignment, the physical properties of a substance versus the chemical properties of a substance, because that's what we're going to need to understand to get, to understand these next few slides. So physical processes often used to separate the components of mixtures. Well, one of them is called centrifugation. Centrifugation, okay? And essentially what you do with that is you spin something. You spin it really fast. And for those of you who are taking chemistry because you are either in the healthcare industry or you want to be employed in the healthcare industry, you're probably familiar with blood samples, right? And so one of the things that's done to a blood sample to get it ready for testing, they do run a lot of tests on blood, right? So before you can run any of those tests, you need the different parts of the blood separated out. And so they use centrifuge. They use a centrifuge, which is the machine that's used, but the process is called centrifugation. But really, it's just you spin it really fast. And so it separates out the different layers based on their density. Okay, and another one probably most of us are familiar with, I know I certainly am, that is filtration. And so that's where you separate out the components according to their particle size or their solubility. And so here's kind of a couple examples of each one of those. So in the engine of a car or any sort of engine, you need air for the combustion, right? That happens in the cylinder, but that's it. You don't want any little dust particles or little leaves or bugs or anything like that in the cylinder that's going to have the explosion, right? So you got to filter all that out. So that's what the air filter is for on an engine. It filters out all of the dust particles, and so that's what we mean by separating out the components according to particle size. But the other thing you could say is filtration is like an extraction, and that's what's going on with coffee. So you have coffee beans up here, and you run hot water through it. Well, some of the compounds in the coffee bean, the ground up coffee bean, are soluble in the water, and some are not. And so the good stuff that you like to drink is what gets filtered through, and that becomes the coffee that we drink, and then the rest of it is left on the coffee filter that you can compost or throw away or whatever you want. So that's filtration. Okay, another one, distillation. That's when you separate out components according to their boiling point. So a couple examples of that. So first of all, you could set up a distillery, and so this is how they make moonshine or really any kind of whiskey that has a higher alcohol content than wine. So, you got the corn mash or whatever, and then you heat it up to a certain temperature where the ethanol, the ethyl alcohol, boils off, but then it cools, and you collect that as it condenses in a separate container. So in the mixture, you've got the water and the corn and other things, and you keep it at a certain steady temperature to where the alcohol boils off. But then over here, it starts to cool off as there's just the surroundings take the energy away, and it condenses into more pure alcohol, and you collect that. Okay, well, the same process essentially is used to purify the different parts of crude oil. So this is how we convert crude oil from the ground into a lot of different products that we use every day. So, just the gasoline that we use in our cars is just one component of crude oil. But, chemicals that we use, like propane, like we talked about earlier. Lots of other chemicals, they just have different boiling points. And so they just get sort of separated out at different places in this apparatus that's used to distill crude oil. So the crude oil goes in, they heat it up, and some of it they can separate out down at the bottom because it has a very high boiling point, but some of it, they separate out up to the top because it has a lower boiling point. So the idea here is that the different components of the crude oil get separated out according to their boiling point. All right, so we're going to move along. So now we're going to talk about different ways to symbolize chemicals, the chemical compounds, and elements in this class, just chemistry in general. So first of all, we have this thing we call a chemical formula. And basically, it is just a way to represent the element or the compound that we are talking about. And so what does it consist of? It consists of symbols from the periodic table, which we'll get into the periodic table more tomorrow. But these symbols are from the periodic table of the constituent elements, and the subscripts are what define the ratio of the atoms of each element in one of the molecules. So, for example, these are two different ways to represent water, H2O.
That's high quality H2O.
Okay, so one way to do it is just with the letters. We got 2 hydrogen atoms. The subscript 2 means that there's 2 hydrogen atoms in every molecule of water. And if there is no subscript, that implies 1. So there's 1 oxygen in every molecule of water. So we can do it just with letters, right? That's one way to represent the chemical formula. But again, we can also represent with pictures. And so there's a couple ways that those are commonly drawn or shown. And that's with what we call the ball and stick model. So H2O, or sometimes the space fill model, okay? So there's just different ways to represent the chemical formula. Okay, and then also we're going to talk obviously a lot about these things called chemical reactions. So what do we mean by that, first of all? Well, a chemical reaction is just the transformation of one or more substances into different substances. Okay, so that's the idea, is that a chemical reaction takes some substances and turns them into other substances. And so the terminology we have for that, which we'll talk more about this in week 2, the original substances, we call those reactants. And then they transform into these new substances, in this case, just one substance and some energy, okay? But they call those products, right? And so again, this is just a different way to represent it. We can represent it with just the letters, okay? And this arrow, if you didn't have figured that out yet, this arrow just represents the chemical reaction. So we have these reactants, then they undergo a chemical reaction represented by the arrow, and they form these products, okay? So we can write them with the letters, like the H2, okay, 2 hydrogen atoms in 1 molecule of hydrogen, O2, so 2 oxygen atoms in 1 molecule of oxygen. Or we can do it with the, so with the letters or with the pictures, either way, we just understand what we mean by a chemical reaction, what it is, and sort of the symbolism involved in chemical reactions. Okay? All right, now, so before we move on, well, actually, let me present this first, and then I'll just kind of summarize. So, ions are another type of substance we are going to deal with. We've already talked about atoms. We've talked about what compounds are, how you have different atoms connected together to make molecules. Those are compounds. But we will also talk a lot about ions. And what we mean by that is particles with a positive or a negative charge. Okay, so some of the terminology. So a cation is something with a positive charge. It's a positively charged ion. So an example of that would be the sodium ion. So the way we represent that is we will put the symbol for sodium, which again comes from the periodic table. I know that doesn't make sense. How do you get Na from this word? So there's no N or A in this word, but the symbol, the chemical symbol, is Na. But remember that scientists didn't always speak English, right? So a lot of this comes from the Latin. Some of the chemical symbols come from the German. But again, we'll get more into the periodic table next week, or pardon me, tomorrow. But this is the chemical symbol, and we represent the fact that it's a positively charged ion with a superscript plus sign, and that's called a cation. And then the opposite type of ion is what we would call an anion, okay? Oh, by the way, so cations, one little trick to remember that is that cats have paws, so cations are positively charged, if that helps. There's nothing cute like that for anions. You just have to remember that it's that anions are negatively charged ions. And so an example of that is the chloride ion, right? So it would be represented with the chemical symbol for chlorine, but with a superscript minus sign. All right. So many different compounds are composed of ions. All right. So let me, again, I want to put something up on the screen here that's not really in your handout. So you may want to write this down just, wherever you have room in your handout. Oops, erase that. Shift E. Okay. So all, matter, a different way to classify matter. A different way to classify matter. Ugh, I'm still getting used to using my little special tool here to help me write on the screen. Is that it can be composed of atoms, right? Is what makes up the matter? What is if I broke the matter down into its simplest units, what can I break it down into? So atoms is one way I could do that, and that would be for a pure element, right? Something that's a pure element. I guess I should write the word pure. So pure element. And so an example of that would be something like gold, like we saw in the flow chart earlier. Okay, so another way that matter, another thing that matter can be composed of are molecules. Okay, and so the type of substance that would be composed of molecules would be a compound. So compounds, that looks like an A, that's really supposed to be an O. Compounds. And so an example of a compound would be water, H2O. Okay, so there are molecules of H2O. And then finally, the other thing that matter can be composed of is what we just talked about, ions. Okay, and so that would be what we're going to get into in tomorrow is a special type of compound called ionic compounds. Ionic compounds. Okay, and a good example of that is sodium chloride. Okay, table salt that you put on your food. Okay, it is composed of sodium ions and chloride ions. All right. Okay, so like I said, many compounds are composed of ions, and so an example would be table salt, just like that. All right. Okay, so now we're ready to kind of move on and talk about some more math. Or what we're going to talk about now is really a setup to learning how to do calculations in chemistry. And one of the most important things we're going to use in chemistry calculations are conversion factors. So we want to talk a little bit about using unit conversion factors. So first of all, what is it? What do we mean by a unit conversion factor? Well, it's a fraction. It's a ratio, right? It's got a numerator. It's got a denominator. And so it's a fraction in which the numerator is equivalent to the denominator. So what's in the numerator is effectively the same as what is in the denominator. So even though they are different units, so it makes the value of the fraction equal to 1.
Hey, this is great, man.
So for example, these two things are equivalent. 1 kilometer is the same thing as 0.6214 miles. They're both measures of an amount of distance, and they are the same amount of distance. And so I can represent them as ratios or fractions. So 1 kilometer is the same as 0.6214 miles. But the nice thing about conversion factors is you can flip them. You can use them however you want, in whatever way you need to get the units to cancel that you want to cancel and to keep the units that you want to keep. So I could also represent this conversion factor as just the reciprocal of this and say, all right, well, if 1 kilometer over 1 kilometer is 0.6214 miles, then 0.6214 miles is 1 kilometer. Okay, so that's the purpose of a conversion factor. Is an equivalency. What's in the numerator is the same as what's in the denominator. Okay, and so here's how we want to use it. We want to use these conversion factors to change units. And so if you want to get rid of some initial units, you're going to use a conversion factor. And the way you want to use it is you want to put the desired units on the top, and you want to put the units that you want to cancel, the units you want to get rid of, on the bottom so that they will cancel. And so you end up with the desired units. Okay. All right. So I think I've got, an example here. So the way I typically do this is I will write it out on the screen first, and then we'll go through it in the PowerPoint just so you can kind of see the solution 2 times. So this problem says, if a car travels a distance of 241 kilometers, what is that distance in miles? Okay, so with a conversion factor problem, you always start with the number that you are given that's not a conversion factor. And sometimes you have to look up the conversion factor. In this particular problem, it's not given, but that's because it was in the previous slide. It was 0.6214 miles is 1 kilometer. So actually, let me write that down. So So 1 kilometer equals 0.6214 miles. Okay, so that's the conversion factor we're going to use. So you start the calculation with what you're given that's not a conversion factor. So I'm given the fact that I've got 241 miles, or pardon me, kilometers. Okay, so 200, pardon my penmanship, I know it's not very good. 241 kilometers. And so as we saw on the previous slide, what I want to do is I want to get rid of those units of kilometers and I want to have units of miles. So I'm going to use my conversion factor in a way that cancels kilometers. So that's going to put kilometers on the bottom. So 1 kilometer on the bottom. And I put the other part of the equivalency at the top. So 0.6241 miles. Okay, so you see that causes my kilometers to cancel. And I have the units of miles. Okay, all right, so I'll erase that and we'll just look at it on PowerPoint. All right, so again, start with 241 kilometers, multiply that times the conversion factor, kilometers cancel, and you get an answer in miles. In this case, they wrote it in scientific notation. You wouldn't necessarily have to do that. It's just, that's how it's represented here. Okay. Okay, now that's the simplest way to do conversion, or the simplest type of conversion factor problem. It actually gets more complicated. So there are many problems that require the use of several conversion factors, but it's pretty much done the same way. You just would tack on another fraction into your calculation.
Prepare to be dazzled.
So for example, let's say we want to convert 3.337 grams per cubic centimeter into units of kilogram per cubic meter. All right, so let's talk about how to do that. And this is just an example of using multiple conversion factors. Okay, so oops, once again, stray marks. Okay, so we always start with the number that we're given that's not a conversion factor. So 3.337. Now the way I'm going to do this is I'm going to put grams, and then remember it's grams per cubic centimeter. Well, there's no reason why I can't just do the cubic centimeter just as on its own in the denominator. It means the same thing as what you see here. Okay, so to keep things simple at the beginning, I'm just going to go ahead and convert grams into kilograms because I'm after kilograms, right? And so one thing I know is just from the metric system, I know that there are 1,000 grams in 1 kilogram. Okay, so my grams cancel. So now I've got the kilograms. I'm good to go there. I've got the units of kilograms, but I need units of meters cubed. But right now I have centimeters cubed. Okay, so here's how we can deal with that. I'm actually going to do it one way, you know, handwritten, and then you'll see it a different way when I show you the PowerPoint solution. But we know, for example, that I want centimeters to cancel. So the relationship is that in 1 meter, I want to keep meters. So that's going to be in the bottom here. And I want centimeters to cancel. So there are 100 centimeters in 1 meter. Okay. But the thing is, that's only going to cancel out one of those centimeters cubed, right? So now that just becomes a centimeters squared because I canceled out one of them and I've got 1 meter. So I have to do that 2 more times. So multiply times 100 centimeters per meter per 1 meter again. And so that cancels another one of the centimeters. So I'm down to 1 centimeter, right? And so I just do it again. Okay, 100 centimeters for 1 meter. Okay, and so finally, all of my centimeters have canceled. And so now I have units of meters, 1, 2, 3. And so when you do that calculation, you just, you know, in your calculator, you would just plug in all those numbers. And so you get some answer and your units would be in kilograms over, you know, meters times meters times meters. So that's the same thing as, you know, kilograms per meters cubed. Okay. So that's one way to approach it. But when I show you the solution with the PowerPoint, you'll see that I could do, essentially you can do all this in one step, but you need to make sure that you understand what's going on if you do it in one step. There's one trick that you have to do. All right. So I'm going to erase all that. And then here's the solution again with the PowerPoint. Better, you know, definitely better penmanship, so to speak. Okay. So once again, we start with the number that we're given that's not a conversion factor. And then I just start converting the units. So change the grams into kilograms. Grams cancel. Now I have kilograms, okay? But now here's the way to do it in one step. So what I want is I want to get rid of centimeters cubed. So I have to cube the conversion factor, okay? But the trick is, the key is you apply that exponent to the units and to the number. So when I put the cubed there, it not only cubes that unit, but it also cubes in this case, 100, that number. It cubes that number, okay? So the exponent 3 is applied to both parts. And it turns out that 100 cubed is 1 million, okay? So 1 million cubic centimeters is 1 cubic meter. All right, so those units cancel, and you get the units that you're looking for. There's your answer, okay? All right, so this example is actually a couple important techniques, I guess you could call it, with using conversion factors. It's using multiple conversion factors. So I had to use the conversion factors of grams to kilograms or kilograms to grams, and I had to use the conversion factor for meters to centimeters. But the other technique that's demonstrated here is how to do conversion factors with exponents. Let's see what comes next. Yes, density. So all of this information about using conversion factors really leads to this topic of density, because in chemistry, a lot of times we'll use density as a conversion factor because it is an equivalency. It's just a ratio of the amount of mass per unit volume, okay? So density is the ratio of the mass of an object or a substance to its volume. So here's the equation, if you want, for density. It's just mass divided by volume. D equals m over v, if you learned it that way. And it's an equivalency. A certain amount of mass is a certain amount of volume for a given substance. All right, and so because of that, because it is an equivalency that relates mass to volume, we can use it as a conversion factor. Okay, so for example, in this problem, we have osmium, which is an element, okay, and it has a density of 22.6 grams per cubic centimeter. And so we are asked what volume in cubic centimeters would be occupied by a 21.8 gram sample of osmium. All right, so, oops. Okay, so let's start the calculation with the number that we're given that's not a conversion factor, 21.8 grams of osmium. Now, again, this is something that I often will harp on with my students. Is it's important to write out the units, because that way you see the things cancel that need to cancel, and you see what units you're keeping, so you know if you're progressing towards the correct answer or if you're off on the wrong track. So now what I'm going to do is I'm going to use that density as a conversion factor to get the grams of osmium to cancel and to end up with units of volume. So the density expressed as a conversion factor, where the volume is on top, is that there's 1 cubic centimeter of this osmium, there are 22.6 grams of osmium. Okay, 22.6 is the density. So in 1 cubic centimeter, there are 22.6 grams. So grams of osmium will cancel, and I'm left with units of cubic centimeters. All right, so that means that I'm pretty much done. I can just plug that into my calculator, and I'll get an answer for the volume of osmium. All right, so it's that simple. So let me erase that, and I'll show it to you with the PowerPoint. Oops.
Ding, ding, ding. What do we have for Johnny?
Okay. So 21.8 grams of osmium, and you just multiply that times the density used as a conversion factor, where I put the 1 cubic centimeter on the top, and I put the mass that is in 1 cubic centimeter on the bottom, and so the grams. And the number that you end up with is 0.965 cubic centimeters. Okay. Another thing to recognize, I don't really put this explicitly in the notes, but remember that a milliliter is the same as a cubic centimeter, right? 1 milliliter is 1 cubic centimeter. They're interchangeable units of volume. All right, so that's an example. Here's your problem. So if you have 2 mils of a liquid having a mass of 3.04 grams, then determine the mass of 30 mils of the liquid. And there's really a couple ways to do this. And so I'm interested to see how you guys think about it and work it out. And I'll break into your groups while you're working on it. So there's a couple ways you could approach it. This is the way that I think about it. So the first thing is I just go ahead and calculate a density based on the information that we're given. We know that a 2 milliliter sample has a mass of 3.04 grams. So 3.04 grams divided by 2 mils would give me the density of 1.52 grams per mil. And so then I can just use that density as a conversion factor and multiply it times this volume of this other sample that I'm curious about. So the sample volume is 30 mils, and so I use the density as a conversion factor so that the milliliters will cancel, and I get units of grams, which is what we were asked for. So